Right, ladies, today we are looking at the effects of intermolecular forces. And the first thing that we are going to look at is the effect of intermolecular forces on the melting and boiling point of substances. Please go back to your exam guidelines and copy down your definitions for melting point and boiling point from there. So, as you all know, melting is when a substance changes from a solid to a liquid, and boiling when it changes from a liquid to a gas. Now, in order for a substance to change phase, a couple of things must happen, as you can see over here. The molecules must be separated, they must move further apart from each other. So these intermolecular forces that are keeping them together must be overcome in order for the phase change to take place. So to explain this a little bit better, I've got an example over here that you can take a look at. So for helium, we've got helium atoms. We know they are nonpolar, so the forces between them will be London forces. Carbon monoxide, between carbon monoxide molecules, we've got dipole-dipole forces because carbon monoxide is a polar molecule. That one's a polar molecule as well. And between water molecules, we'll have hydrogen bonding forces. Now, take a look at the values over here. And of course, you don't have to go learn them. So we can see that the melting and boiling point of helium is the lowest, and the melting and boiling point of water is the highest. So from this, we can see that the stronger the intermolecular forces between the particles, more energy is required to overcome the intermolecular forces and to separate the molecules so that a phase change can take place. So in other words, if I have a substance with a very high boiling point, for example, it means that there are very strong intermolecular forces present between the particles. Right, and then something else that we have to look at over here as well is the effect of molecular size. There is a table on page 87 of your textbook that you can go look at. So I've just taken an example from there once again. So I've got helium atoms here once again, and over here I've got oxygen molecules. Now helium atoms are nonpolar, oxygen molecules are nonpolar, so the intermolecular forces here as well as here will be London forces, and we know that they are weak intermolecular forces. But once again, if we compare the melting and boiling point of helium and oxygen, we can see that oxygen has a much higher melting and boiling point compared to helium. And that shows us that the melting and boiling points of substances consisting of smaller molecules or atoms like helium is lower than that of larger molecules, the oxygen in this case over here. Right, and then the next thing that we have to look at, density. This is quite simple and straightforward. Density is the number of atoms per unit volume. In a solid, we've got the highest density compared to a gas where we have the lowest density. And that would also mean that in a solid, we'll have stronger intermolecular forces compared to a liquid, and the weaker intermolecular forces will be found between the gas particles. Right? Then thermal expansion, the change in volume of a substance with an increase in temperature. And to try to explain that, I've done the following. Let's say we've got two substances. Substance A has dipole-dipole forces between the molecules, and substance B has London forces between the molecules. Now we know that dipole-dipole forces are stronger intermolecular forces compared to London forces. So for substance A, more energy will be needed to move the particles apart compared to substance B. So that is why at the same temperature, substance B will undergo more thermal expansion compared to substance A, because substance B needs less energy to separate the particles. So we can then also say for a given temperature change, thermal expansion will be greater in gases compared to liquids, because in gases we've got the weaker intermolecular forces, and greater in liquids compared to solids, because in solids we've got the strongest intermolecular forces, which requires the most energy to overcome these forces. Okay, thermal conductivity, a material's ability to conduct heat energy. If we compare metals and non-metals, we usually say metals are good conductors of heat. Why is this? The atoms are held together in a three-dimensional network, there's strong bonds, and the vibrations can pass quite easily from the one particle to the next because they're so close together. Compare that with non-metals, which we usually describe as bad conductors of heat, small covalently bonded molecules, weaker intermolecular forces, so the molecules are not held as closely together, so it's not that easy for the vibrations to be transferred from the one to the next. So generally, non-metals are described as bad conductors of heat. There are exceptions to the rule, of course. Graphite is an example of a non-metal that is a good conductor of heat. Okay, viscosity. That is the resistance of a liquid to flow. And what you need to know here is stronger intermolecular forces would mean that it would be more difficult for molecules to move past each other. So substances, liquids with strong intermolecular forces will have a higher viscosity. Also just take note that it's not just intermolecular forces that determine viscosity. The length of the molecule also plays a role, because if molecules are very long, they can become intertwined, and that also makes it difficult for them to flow or to be poured. And there's a very nice illustration on page 89 which describes or explains the whole idea of viscosity. So please go take a look at that. And then vapor pressure is something that you don't have in your book, but it's definitely in the guidelines. So I just want to say a couple of things about that. It is described as the pressure exerted by a vapor at equilibrium with its liquid in a closed system. So to try and explain that, let's take a look at this. As you all know, if I take a beaker with water and I leave it outside for a while, evaporation will take place and the liquid will change from a liquid to a gas. Now, if I do this again, but I place something on top of the beaker to make sure that the gas particles can't escape, the following is going to happen. So, evaporation, particles will go from a liquid to a gas, and then as the number of gas particles in this space over here increase, they will start colliding with each other and the sides of the container, and eventually some of these particles will go from a gas back to a liquid, which means that condensation is also going to take place over here. Eventually, we'll reach a stage where the rate of evaporation is equal to the rate of condensation, and we then describe this as dynamic equilibrium. So, this gas in the space over here also exerts a pressure on the liquid. So if we go back to our definition, the pressure exerted by a vapor at equilibrium with its liquid in a closed system. So that's explained quite nicely there. So those gas particles there exert a vapor pressure. And then just to bring in intermolecular forces, take a look at this example over here. Over there, I have got a bottle with water, and there I've got a bottle with carbon tetrachloride. So, we know that water molecules are polar, and the intermolecular forces there will be hydrogen bonding forces, which are very strong forces. Compared to that, carbon tetrachloride, those are non-polar molecules. So, between them, we'll find London forces, which are weak forces. So because of the weak forces here, it's quite easy for these particles to go from a liquid to a gas. And that is why, where we've got weak intermolecular forces, we'll have a high vapor pressure, compared to over here, where the intermolecular forces are stronger, keeping the particles together. So strong intermolecular forces will go with a lower vapor pressure. And then the last thing that we just have to look at is solubility. And the rule that we use here, if we want to decide whether something will dissolve in something else, is like dissolves like. So a solute is more likely to dissolve in a solvent with a similar chemical structure. So let's take a look at this example. Over here, I've got some iodine crystals in water. Now, water, as we know, polar molecules, strong intermolecular forces, hydrogen bonding forces. The iodine, non-polar molecules with weak intermolecular forces. So here I've got polar molecules, non-polar molecules. I've got strong forces, I've got weak forces. So like dissolves like definitely doesn't apply there. So that means the iodine will not dissolve in the water. Over here, I've got iodine once again. So non-polar molecules, weak London forces, but I've got carbon tetrachloride, which is a non-polar molecule. So weak intermolecular forces, London forces between the molecules. So I've got non-polar molecule, non-polar molecule. I've got weak intermolecular forces. I've got weak intermolecular forces. So like dissolves like most definitely. And what is going to happen? Definitely the iodine will dissolve in the carbon tetrachloride. Right, ladies, so I think that is enough for now. Thank you.